It's my pleasure to welcome Ravi Netravali, who is assistant professor at Princeton University and who received this year the SIGCOMM Rising Star Award. So the SIGCOMM Rising Star Award is an award that was invented by CoNEXT to recognize young researchers who have already a high impact in the field, and so to encourage the young researchers to make more progress in their research, in contrast with the SIGCOMM Award, which is mainly for senior researchers who have a long experience in research. So the Rising Star was to encourage young researchers who are having a high impact. And Ravi is the one who was selected this year by the SIGCOMM Award Committee. So he will give a keynote on application-centric networking. And unfortunately, the keynote is remote, but Ravi will give his presentation, so you see him live. And after the presentation, we will have discussions, and I hope that we will have, with the microphone, everything should work perfectly. So Ravi, the floor is yours.
Sounds great. Well, thank you very much for the introduction, and thank you all for coming. It's my honor to be speaking to you today, and I'm sorry that I couldn't be there in person, but I'm sure the conference is going to be wonderful, and I hope to see many of you in person soon. So today I want to talk about some exciting opportunities and directions at the intersection of computer networking and applications. So let's dive right in. So the internet has undeniably been one of the most revolutionary and influential technologies over the past few decades, serving as this ever-growing bridge between people, communities, and geographic locations. And if we really reflect on what the internet has brought us, a big aspect is tied to the distributed applications that we run on top of it for things like healthcare, news, education, social networking, and more. And it's really through these applications that people are typically communicating with each other and exchanging information. And indeed, this is probably relatively unsurprising, hopefully, but most traffic on the internet today is generated by these commercial applications with things like video, mobile applications, gaming, and others, right? These are really the endpoints in typical internet communication today. And yet, despite this dominance of internet usage and resources, applications actually have a fairly small footprint in the networking community, right? So in classrooms, we teach, networking as the stack of layers with, popular protocols at each one. And it's true that at the top, the layer is labeled application. But in my experience in both taking and teaching networking classes, that layer gets fairly minimal attention. And it's really focused more on protocols like HTTP rather than how applications as we know them actually work and use those protocols. From a research perspective, the picture's a little bit better, right? But it's still skewed away from the internet's reality. So just looking at the sessions and papers at SIGCOMM and CoNEXT over the past few years, only a very small fraction are really application-centric in that they're deeply motivated by specific application use cases or involve, changes or co-designs with applications. And that's not to say that the other fantastic work that appears at our conferences, doesn't somehow benefit applications indirectly, right? It's more so a statement of the focal point of our research endeavors and the motivations for our work as a community. And so my goal in this talk is to convince you that we, as the networking community, should reconsider how we think about applications and actually bring them into the purview of what we do as networking researchers, rather than viewing them as these separate entities that are owned and operated by other communities. And so why might that be helpful? Well, applications and networks clearly interact with one another, and they have lots of shared problems, but they provide different vantage points, capabilities, and insights. Right? So on the one hand, applications ultimately define the workloads that we face in the network. And they also present control knobs for tuning those workloads. On the other hand, the network clearly has more visibility into things like cross traffic and telemetry for example, finding the root cause of a certain delay. And so taking these things together, thinking about applications and networks more holistically can provide many new opportunities for us as networking researchers. For instance, application knobs can be a rich source of solutions to mitigate, or in some cases even sidestep, certain networking challenges that are actually tough to solve lower in the stack. Similarly, applications can provide meaningful ways to leverage advances in core networking, ranging from the improved telemetry that I just mentioned to improved hardware speeds and programmability. Yet, despite these potential benefits, you may be asking, why now, right? We've probably heard these things dating back to, things like active networking or, interfaces for specifying traffic priorities that have all sort of struggled to gain traction, right? So what's different here? Well, first, we're facing an increasingly pressing need to cope with high application traffic, right? So more and more users are getting on the internet and using applications that are increasingly heavyweight as they evolve to take advantage of what the internet has to offer resource-wise. And so, for example, if you look at video streaming over the years, we moved from these flat 2D videos to these panoramic 360-degree videos, now to these volumetric point clouds that we try to stream. And surely the functionality and experience is getting better with this evolution, but so too are the resource costs. They're getting much, much worse. At the same time, we increasingly cannot rely on just lower parts of the stack to deal with these networking challenges. So at the end of things like Moore's Law, network devices aren't getting that much faster. Designing accelerators is not an easy thing to do, nor is it a fast task. And applications evolve much faster than lower parts of the stack do. And so there's really only so much we can do from within the network to solve these types of resource challenges. Instead, I'll argue that we need to start rethinking broader parts of the stack to address these networking issues and achieve good performance. And in particular, this talk is going to focus mostly on a proposal for networking research that centers on how we can rethink applications and their interactions with the existing network stack to address many networking issues. So what would that take? Right, so clearly we need ways to dive into applications to understand their behavior, the knobs that they expose and their network usage. And then we somehow need to be able to link those insights to network operation and network decisions. And rather than saying that we all need to become experts for every application domain and deployment scenario, which is just untenable, I'll instead present a methodology that my collaborators and I have used and followed over the years to address these needs by leveraging advances in several other CS disciplines. So for example, there are now a wide range of lightweight tools for automatically understanding application behavior, ranging from things like static and dynamic program analysis for traditional programs to video feature analysis to analyzing entropy and activations in machine learning. There's also now a flurry of data-driven algorithms that can help us automatically link application and network logs and insights across all these different deployment scenarios, rather than us having to do this manually. And so in the rest of this talk, what I want to do is walk through just a bunch of examples to highlight the potential benefits of this methodology and how we've used it over the years to solve a variety of network-related issues. And I'll sort of structure this to mimic my own journey with this approach, from the time that I started as a PhD student to now. But this also mirrors how common applications have actually evolved over the years, shifting from these traditional web applications to, heavily relying on video data and to more recently embedding all kinds of machine learning powered functionality. So let's start with the web case. So when we started working on this problem maybe 10 years ago, there were lots of these different headlines that you've probably seen highlighting, how page loads were really slow and how even milliseconds of delays, could frustrate users and have all kinds of business implications. And so our work on this topic really just started by trying to understand why page loads were staying so slow, despite so much web performance work that had been done and the faster and faster networks and devices that we had. And so if you look at a page load, what actually happens, right? So say we want to load this simple page with 3 files. A browser would first fetch the top level HTML, and it would parse it tag by tag, discovering that it needs some JavaScript file. So it'll fetch that script and execute it. And along the way, it would fetch a referenced image. And once all of these objects have been loaded and rendered, the page load would be called complete. But it turns out that even though this is fairly intuitive, it's actually a highly inefficient process. And the reason is because neither the client's browser, CPU, nor its network are really actually being fully utilized. Right? So here, the gray areas represent times where the network's being used, while the green boxes are the times where the CPUs are being used. And as you can see, there are multiple times where the browser is using CPU resources, but keeping the network idle as it decides what to fetch next. And the reverse is true too. And so the crux of the problem here is that serialization in the page load process between tasks involving the CPU and the network lead to significant resource underutilization and slow page loads, even with fast networks. And so the key then to solving this is to try and reorganize the page load process to better use the CPU and network. And so we've done a bunch of work to alleviate this inefficiency, and I'll cover a few examples in the coming slides. But the common theme that I want to call out is our use of what we call detailed dependency graphs that capture not only what files reference other files like the graph here, but also details like how those files share state, which we collect using different program analysis techniques within the web applications themselves. So for example, here, we can see that this HTML file writes to a variable that the JavaScript file reads. And so we better make sure that the JavaScript file is executed only after the HTML file is executed. And so we can add this type of edge to the graph to capture that dependency. And of course, real world pages have far more complicated graphs, but the important bit here is that application details actually shed light on how we can reorganize different page load tasks and what rules we really have to respect to avoid breaking applications. So how might those graphs be useful? So starting at the beginning of the page load process, right? The first thing we have to do is fetch the top level HTML file, and that can actually end up taking hundreds of milliseconds. And this is particularly troublesome because during this time, browser screens are typically blank, even if other files are actually already in the browser's cache. Right? The issue is that HTML files ultimately specify what must be loaded for a page, but they aren't cacheable since they typically bundle together static content like page layouts with dynamic content like the latest headlines. And so until we actually get that HTML file, we can't really make effective use of the network or CPU. And so our goal with the system called Fox was fairly simple, right? Where we wanted to essentially reorganize the early part of the page load to overlap the processing of static HTML content with the fetching of just dynamic content to better use these CPU and network resources. So Fox works in three main phases, right? We first have to analyze the potential HTML files to extract what we call a template of static content that's shared across the HTMLs and can be cached in a browser. Then during page loads, we have to figure out a list or what we call a patch of operations that convert that template into the latest version of the page. And then finally, we have to download that patch and apply it to the template that's already been loaded by the client browser. So I won't go into all the details, but I'll focus primarily on phases 1 and 3. And what I really want to highlight is how important these dependency graphs and application introspection tools are in letting us actually realize this type of reorganization without breaking things. So in phase 1, given a set of potential HTML files, Fox essentially uses like a modified tree matching algorithm to highlight the differences between these different trees, which you can then actually post-apply to find the similarities. And so this actually gets us most of the way there to a static template, but it's not enough. The main challenge comes down to fine-grained state that's read by JavaScript in the page and issues with this reordering. For instance, here, we've kept this script tag in the template in the blue graph since it was in both HTML versions. But remember that templates are going to execute now fully before any patches are applied. And so if this script were to, for example, find all objects with ID X, well, now it's going to get an empty result when in the real page it would have been returned this span tag whose ID we actually removed, right? Because it wasn't common across these two trees. And so it's crucial to use these dependency graphs and program analysis techniques to make sure that templates stay internally consistent, in that JavaScript code that we keep in the template cannot depend on any HTML state or JavaScript state that we've removed. And so here we'd actually have to remove that script tag. And this problem arises later when we try to apply patches as well, right? So here, imagine that we've executed this template and we've already downloaded the patch that we want to apply, right? So let's say that this gray tree is the template's HTML. And this patch tries to insert a JavaScript file in the middle of the page that searches for image nodes. So now we have a reordering problem again, right? Because if we run the script normally, it's going to return these two images. When during a normal page load, only one of them, which is the blue one, actually would have been observable based on how browsers actually parse HTML. And so to deal with this, we need what we call view invariance, which basically means that JavaScript files in the patch only see the page state that they normally would, despite the fact that templates are fully loaded. And so we use these dependency graphs that I described and some custom wrappers around these browser methods to actually enforce that. And then we can make sure that the return is correct. And so we found that Fox's approach to actually going deep into web applications to reorganize things was quite effective at speeding up the first part of page loads. But there's still a lot left in the process, right? This was just the first step. And so going back to our load process from earlier, what we saw was that the big problem is this resource underutilization due to serialization between evaluating files to figure out what to load and then actually fetching them. And so a natural solution to this would be to basically decouple those tasks. And in fact, there are multiple mechanisms that had made their way into the HTTP standards for this, with the two most popular ones being server push and preload hints. So with server push, servers can proactively send files to clients before they're actually requested, while preload lets servers embed URLs for third-party resources directly into HTTP headers so that clients can immediately go request those files when they receive a response, rather than first having to parse the response body. And so these mechanisms have been around for maybe a decade or so, and many studies have shown that they can be very effective, but their adoption in practice has been quite limited. And the main reason is that they can actually end up hurting performance if they aren't configured with cross-stack awareness of the page, the network, and the compute setting. So as an example, in this experiment, we basically started with the baseline execution environment at the bottom of the slide, and we performed a brute force search to find the best push preload policy per page. Then we varied just one property in the environment. So in this case, we changed the CPU from 2.2 to 1 gigahertz. And again, we found the best policy per page in this new target environment. And finally, we compared in the target environment the best per page policies from the from the baseline environment, from the target environment, and also a default browser. And as you can see, even this minor edit to the environment actually made a pretty big difference, right? With the best policy for the target environment doing better than the one from the baseline, which in fact does worse than a default browser, so it actually hurt things. And we found that these trends held as we varied other parts of the environment as well. And so to handle this, our solution, which we called Alohomora, basically just tries to learn how best to adapt these policies at runtime by jointly considering aspects of the page, the network, and compute resources. So in particular, Alohomora represents its policy generation logic as a neural network that it's trained using reinforcement learning, which we find actually proves to be an expressive and also automated way of representing and linking these subtle cross-stack relationships. So how does that work? So generally, with reinforcement learning, the idea is for a learning agent to interact with an environment. So at each time step, the agent observes some state from the environment, and it takes an action. And as feedback, the environment will return a reward signal to the agent, which essentially indicates how well that action performed. And the goal of the learning agent is to maximize the total reward that it receives from the environment. And so following this general reinforcement learning paradigm, our environment would be a page load setup, while the state space will include information summarizing the network, the device, the browser, and also the page using these dependency graphs that I described earlier. Our action space is going to be a set of potential push or preload decisions, or really it's a running policy of those decisions. And the reward is whatever web performance metric that we want to optimize for. And inside this learning agent, we're going to put a neural network that maps those state inputs to a probability distribution function over the action space, which basically specifies what action to take next. And we can then train that neural network using standard stochastic gradient descent. And so with this setup, overall, Alohomora was actually able to more than halve page load times. And more importantly, it never, in our experiments, slowed things down, unlike previous policies, including our own, that were sort of statically configured, and they lacked this cross-stack awareness. And so this is sort of a testament to the ability of how carefully crafted data-driven strategies can actually help usefully fuse together and jointly analyze application or page level characteristics and network characteristics to deliver better performance. So just to recap a little bit, we've just discussed two web optimizations that highlight the potential benefits of our two-pronged methodology, right? So going deeper into applications to reorganize operations and avoid network issues, and also with Alohomora using machine learning techniques to fuse together observations from applications and networks so that we can make more informed application decisions. So I will now transition a little bit into the next phase of our journey, which focuses on the big class of video applications that have come to dominate internet bandwidth. And in particular, I'll focus mostly on video streaming on demand. So things like downloading YouTube videos rather than real-time conferencing applications like Zoom. So our motivation for studying video streaming actually mirrors our motivation from the web case, right? Where users impose these fairly high performance expectations, right? So for instance, studies have shown that users will often leave videos if they take more than 2 seconds to start playing, or if they have too much stalls or rebuffering during the playback. And so how do these applications work and actually manage user perceived performance? So at a high level, many use dynamic streaming algorithms over HTTP with frameworks like Dash. So in these frameworks, to load a video, a client will essentially periodically request individual chunks of videos from a video server, with each chunk representing several seconds of video content, and each chunk can also be requested at one of several bit rates or quality levels. And as the video chunks are downloaded, they're stored in this playback buffer that's going to be drained in real time as the user watches video. But that buffer is only going to be populated at a variable rate, since it depends on the bit rates that are selected and the current network conditions, particularly bandwidth. And so this can be problematic, as you see here, right? If the chunks that we request have higher bit rates than what the network can support, our queue is, of course, going to drain faster than it fills, and then we'll ultimately reach an empty buffer and have a stall in the playback. And so to prevent issues like this, video players use what are called adaptive bitrate algorithms, or ABR algorithms, that decide both when to download chunks and at what bit rates. And so the goal of these algorithms is to use an understanding of what the network can support, and then to select bit rates that are projected to maximize overall performance for users. And so that seems fairly intuitive, but what's hard about it? Well, there's a few key difficulties. So first, to make the decision for the next chunk, we have to have a sense of what the network will look like during that chunk's upcoming download. However, there are far too many possibilities for this. And past throughput observations aren't always great indicators about what's going to happen next in these different scenarios. Right? So we somehow have to deal with the uncertainty in what the network can support. Second, we have to balance a bunch of different quality of experience goals whose optimizations can actually be conflicting at times. And third, each bitrate decision can actually have an implication on future ones. And so for example, if we use a high bitrate at the current time, the delay in downloading that chunk may actually lead to depleting my video buffer. And even if we don't ultimately stall, the smaller remaining buffer leaves us with limited cushion to deal with future network uncertainty and upcoming decisions. And so ABR algorithms really have to plan for the future. And so to deal with all of this, the key is in figuring out how to make application bitrate decisions in a way that ensures high performance despite the uncertainty in the upcoming network forecast. And so our solution, which we called Pensieve, basically tries to automatically learn the right way to balance and jointly analyze those cross-stack elements to make performant bitrate decisions. And so just like with Alohomora in the web context, we used reinforcement learning here as this generic platform to learn these kinds of sequential decisions. So here, our environment is a video streaming environment. And our state space, again, includes information characterizing both the application, in this case, the video player state, so including things like current buffer occupancy, as well as information about the network with things like sizes and download times for recent chunks, which are essentially time series of observed throughputs. The action space here lists the bitrate options for the next chunk, and the reward includes the various facets of quality of experience on the previous slide, so things like bitrate or quality levels, as well as rebuffering. And finally, we again have this neural network in the middle that kind of links these cross-stack state signals to the actions. And we can train this as our ABR algorithm that ultimately determines the bitrate to use for the next chunk to download. And so Pensieve performed pretty well, and I'll show some evaluation results in a few slides. But in the 6 years since we worked on Pensieve, video streaming applications themselves actually underwent a pretty significant paradigm shift towards this world of short video streaming applications like TikTok or YouTube Shorts that I'm sure many of you use. And although much of the ecosystem and performance metrics for these applications are similar, the key difference with short videos is that the expected user behavior is to actually have lots of fast switches between videos based on user swipes. And so from the perspective of video streaming algorithms, this leads to two big differences compared to the basic framework that I described with Pensieve. So first, some parts of a given video may be totally skipped. And second, video chunks may not always be played sequentially, right? And so this warrants a new type of design. So intuitively, an ideal way to deal with swipes in short videos is to download and buffer chunks out of order. So for example, here, when a user is watching the first chunk of video 1, it may actually be wise to download the first chunks of videos 2 and 3 before downloading the remaining chunks for video 1, right? Since we'd then be prepared for cases where the user abruptly swipes and we could actually avoid some rebuffering. But that's not actually what standard streaming algorithms like Pensieve do. Right, so instead, they typically assume that videos are going to be watched to completion in order, and so they buffer chunks sequentially from video start to end, which actually ends up leading to substantial rebuffering and wasted data in short video scenarios. So for instance, here, an existing algorithm would have downloaded all of video 1's chunks before touching video 2. But if a user swipes during video 1, not only are we wasting bandwidth on these chunks that now aren't going to get watched, but we're also going to incur rebuffering at the very start of the next video, which unfortunately is right after a user interacted with the application. And so while algorithms like Pensieve help us tackle network uncertainties by carefully selecting bit rates, they aren't really equipped to deal with this new wave of uncertainty from the applications themselves. And for this, what we really need are new complementary algorithms for determining what order to buffer or download chunks in to cope with these different potential swipe patterns based on application and network state. And so to address this, our solution, which we call Dashlet, essentially draws on insights and constraints from how short video applications actually work. So in terms of constraints, there's sort of two main ones that short video applications mandate that are fairly intuitive, right? So first, just like normal streaming, later chunks in a video are only reachable by earlier ones. And second, later videos are only reachable via swipes from earlier ones. And so these actually get us most of the way there with regard to buffer ordering priorities, right? Since we know that, let's say, we were at watching currently the first chunk of video 1, chunk priorities would essentially decrease in terms of buffer priority as we move either to the right or downwards. But what this doesn't tell us is how to deal with scenarios where priorities really depend on when a user specifically is going to swipe. Right? So for example, these types of decisions in red where we're debating between the next chunk in the current video versus the first chunk in the next video. And so to help with these decisions, we turn to patterns about how users actually commonly interact with short video applications. So in particular, we conducted a user study with participants, both from our campus as well as many people on Amazon Mechanical Turk. And sparing you all the details of the setup, the big takeaway was that swipe distributions for a video are relatively stable across users, right? With users likely swiping at similar parts of the video, based on the specific content that's being displayed. So certainly these are not formal constraints, but the swipe distributions end up giving us a stable enough signal about how likely swipes are and will be in a given video, and more coarsely at what part of the video they're going to occur, which we can then use to prioritize the remaining chunks. And so what Dashlet does is it essentially removes the idea that playing start times are monotonically increasing across sequential chunks, and instead it just views those as random variables. So for instance, here, the playing start time for the second chunk of video 3 would be a random variable, right? Since it essentially is the summation of the times that a user swipes in video 1 and video 2, both of which are random variables modeled by the distributions on the previous slide, as well as the duration of video 3's first chunk. And so building on that intuition, Dashlet's buffering algorithms work in 2 steps. So first, for the various candidate chunks that we could buffer at any time, Dashlet calculates a distribution for their playing start times, and it represents those as these continuous functions. And those are then fed into a greedy heuristic that ultimately selects a buffer order for the upcoming time horizon that's expected to minimize rebuffering delays across different potential viewing sequences and given a potential forecast for the network. And I should note, finally, once the buffer order is selected with Dashlet, it then essentially just uses existing bitrate selection algorithms like Pensieve to pick quality levels for each chunk. So, both Pensieve and Dashlet were able to deliver substantial improvements in quality of experience on different networks as compared to a variety of alternative algorithms in each domain. So, for example, different rate and buffer-based algorithms with Pensieve. And also in Dashlet's case, we compared with TikTok. But instead of really emphasizing these numbers, what I really want to stress here is how these wins are really, again, a result of this 2-pronged methodology, right? Showing us how, on the one hand, we could link video player and network state to make performant bitrate decisions, while on the other, we found that going deeper into applications themselves, in this case, short video applications, could actually help us cope with their fast-paced evolution rather than solely relying on doing this, from far lower in the stack where things are harder to change and we lose a lot of that application visibility. All right, so moving to the last piece of our journey, we've undoubtedly seen a crazy, unprecedented wave of machine learning and AI being embedded into distributed applications in the form of chat assistants, augmented reality, and so on. And for some continuity here, I'll focus on video-related machine learning systems, and particularly I'll focus on machine learning inference in these applications. But my group has done a bunch of work on these using very similar principles to tackle issues in things like distributed machine learning training or natural language processing applications that I'd be more than happy to talk about. So in the space of video analytics, right, real-time analytics have been crucial in enabling and guiding a wide range of applications, ranging from drone systems for smart agriculture or drug delivery to traffic analytics. And at the heart of those various video analytics applications are really machine learning pipelines for executing analytics queries. And so in these pipelines, camera feeds are streamed to a set of servers that often have onboard GPUs. And there, different machine learning models, which are usually convolutional neural networks in this case, run on each frame in real time with the goal of trying to locate and characterize different objects in the scene. Right, so these servers could be running across the wide area somewhere in the cloud, or more commonly these days, they could be at the edge where they're actually only separated from the camera by a few hops, usually including at least one wireless one. And the goal with these pipelines is to maximize query accuracy, subject to both latency goals from applications, right, since we want real-time processing, as well as the availability of different network and compute resources. And very quickly, as these pipelines became more popular and more and more cameras were being deployed and streaming very high frame rates, the networks that were connecting these data sources and processing servers quickly became the main bottleneck in preventing fast analytics responses and achieving these different goals. And so given that we're dealing with video data, a natural solution is to sort of capitalize on the redundancies between video frames, right? Much like how video encoding works in the first place. But even though this is a pretty simple idea, doing this for analytics is actually a little bit trickier than, say, for lossless encoding, where humans are the main consumers of videos. And in particular here, machine learning models and analytics queries are actually the consumers of the video content. And the big question that we have to answer is, what level of redundancy is actually sufficient to ensure that we don't bring accuracy degradations to our target model and query? And so just to illustrate this challenge a bit, consider these 3 example frames and a query that's trying to count people in the scene. Right, so here, our model returns the following results, these 3 results, which suggest that it actually would have been OK to filter out either the first or the second frame, since they're back-to-back and they give the same result. However, if we now consider a slightly different query that's actually counting cars in the scene, things look a little bit different. Right, so we wouldn't actually be able to filter the first frame, and instead our only options would be to remove either the second or the third frame, which in fact are actually less visually similar to one another. And this gets even worse when we start to worry about different query types, like detections that are looking for bounding box coordinates, or if we start to worry about the nuances between how different models operate even for the same queries. And so ultimately, it's not really clear how to make such safe filtering decisions, short of actually running the model and the query and then comparing the results, which defeats the purpose of filtering. And so to tackle this challenge, the main insight behind our system called Reducto was that low-level video features could help us here. Right, so these features, such as basic pixel differences or area features that are looking more for bodies of moving pixel densities in the scene, are basically just another form of application introspection techniques from the computer vision community. And what's nice is that in addition to being super cheap to extract, we found that even though these features are really just tied to video data rather than anything about machine learning models or queries, they actually give us enough of a signal to make smart and careful filtering decisions. So in particular, we found that the changes in these feature values end up being highly correlated with changes in query results, which is actually the heart of filtering decisions in the first place, right? Since logically, as we saw on the previous slide, we can remove any frame that has the same result as the previous one, since it's not really contributing any new analytics insights. There's no free lunch, though, right? So the biggest issue that we still have to decide is, what degree of change in feature values means that we can safely filter out a frame for a given scene and query. Right, as you can see here, even for just one query type, the optimal threshold for feature values, which is the one that filters the maximum number of frames without losing accuracy, really varies across scenes and over time. And so what our Reducto system does is it automatically learns the appropriate time-varying thresholds by using some high-dimensional clustering techniques on the latest frames to relate feature values and thresholds to analytic results and network conditions. And so this analysis is continually run on incoming frames, but periodically the server will share some results of this processing with cameras in the form of just specifying what feature to use and what threshold to use for a given query, so that cameras can then just do really lightweight filtering locally. And this was sort of a big goal for us, was trying to run on already deployed cameras that don't necessarily have, say, onboard GPUs. Of course, I've allotted a bunch of details around things like when to update filtering rules or how to perform efficient encoding now that we are filtering. But this is really the heart of our solution, which not only goes deeper into the application, but actually automatically links those findings with network characteristics to improve accuracies and alleviate network bottlenecks. And the effects were pretty significant. So across a bunch of different queries and video scenes, Reducto was able to filter between 50 to 80% of frames, which resulted in 25% reduced bandwidth usage after encoding. And this is where things got a little bit interesting. So I mentioned earlier that processing servers for video analytics had steadily been moving towards the edge to bring, lower latencies and in some cases, improve data privacy. And so at first, since cameras were still typically separated from these edge servers by wireless networks that weren't terribly well provisioned, the bottleneck was still most often in frame transmission over the network. But as more and more encoding and filtering techniques like Reducto were developed, this bottleneck steadily shifted to another kind of network in the form of on-path processing and data movement within the edge servers themselves. So what do I mean by this? Well, video analytics workloads are typically executed just like any other model inference serving platforms, right? So as frames stream in, different models are sequentially executed on the frames in real time. And in order to process a frame with a certain model, that model's weights need to have been loaded into GPU memory. And these weights are essentially the values that parameterize the model's different layers of computation. And they actually end up accounting for most of the model's size in terms of memory. Right? So to run these workloads, all of these models need to have been loaded into GPU memory. And this actually proves to be a problem. Right, so we analyzed some real-world video analytics deployments and found that they're already at the point where the total amount of GPU memory that's needed by the models in these workloads exceeds the memory that's available on edge servers. And this will only get worse, right, as the number of cameras grows and as workload sizes grow, just as more and more applications start to use this kind of machine learning analysis. And so one way to deal with this insufficient GPU memory is to timeshare the model's execution in the GPU by basically just swapping models in and out of GPU memory. Right? So you could use any off-the-shelf swapping scheduler that you want, but basically when there's not enough GPU memory to concurrently hold multiple models, the models are just going to be continually funneled between CPU memory that's usually more abundant and this restricted GPU memory. And so this makes sense. But it ends up not working out because of model transfer delays in the edge servers, which are typically far too high relative to the real-time processing needs that we have. And this ends up resulting in lots of skipped frames for processing and then big accuracy drops. Right, so for example, if we're targeting real-time processing for 30 frames per second, we essentially have 33 milliseconds to load and run models. And yet, if you look at this table, even just the time that it takes to load one model into GPU memory exceeds that budget in many cases. And so digging deeper, the main issue is that the PCIe links connecting CPU and GPU memory in these edge boxes are only a few gigabits per second, which is just not enough given the types of model sizes that we're seeing today and our tight time budgets. And so short of designing new edge GPUs with substantially more memory, which is hard given their tight form factors, or better provisioning PCIe links, which are just very expensive, what else can we do about this GPU memory bottleneck? So the main insight that we had was that if you actually look closely at what these different models are doing, they're operating on the same input, which are images, and they're performing mostly the same common operations, such as image processing tasks like convolutions or machine learning operations like pooling. And so as a result, many of these models have many identical layer definitions. And by layer definition, I mean the actual computation or function governing a given layer, not the specific weights. Right? So for example, if I took the same model and I trained it on two different data sets, of course, the weights would be different in the two cases, but the definition for every layer would be shared across those two models. And it turns out that even models from different families have a substantial number of shared layer definitions. And if you're interested in better understanding why these common layers arise or the role that they play in these different models, definitely check out our paper, which analyzes this in a lot more detail. But for now, what does this observation about shared layer definitions even do for our GPU memory issue? So let's say for a moment that we were not only able to find shared layer definitions across models, but we could actually also find a shared set of weights for those common layers. So if we go back to our setup from earlier, this brings a few big advantages. Right? So first, more models can just fit concurrently into GPU memory, right? Since only one copy of these unified weights needs to be stored and loaded per shared layer. And so as a result, fewer model swaps are actually going to be necessary. And second, we've reduced the time that it takes to load additional models because you no longer have to load all of the layers, but rather just the ones that aren't shared. And so both of these wins are really just coming from the number of parameters that we store and load per model, and the promise is pretty high, right? So for the workloads that I showed earlier, we could actually shrink memory overheads by up to 86%, which would let us process just far more frames. But doing this in practice has two big issues, which is what our GEML system tries to solve. So first, there's an inverse relationship between the number of merged layers and the achieved accuracy during retraining, since when you merge a layer, it's not only difficult to have it use shared weights that capture its functionality across the different models, but it also means that each model has fewer other layers to play around with to cope with that new constraint. And so our main observation here was that memory is routinely unevenly distributed in these models. And in particular, the steep slopes here correspond to what we call heavy hitter layers, or layers that consume a large proportion of the model's memory. And so these layers are typically responsible for condensing low-level features to higher-level ones. But what's important here is this means that we can actually, rather than trying to just share as many layers as possible, we can prioritize just merging these few heavy hitter layers to get big memory savings while avoiding pretty serious accuracy degradations. And second, it's actually quite expensive to determine if a given set of merged layers is even feasible from an accuracy perspective. Since I'm running slightly low on time, the brief summary here is that we found that we could actually train these layers for merging independently, where the success of one layer being merged doesn't depend on other layers being merged. And so I won't go into the details of the GEML retraining methodology, of course, but at a high level, it follows these principles and it does this greedy merging process where it really prioritizes these heavy hitter layers and adds them one at a time to the configuration. And the results were pretty powerful, with 60% lower memory overheads and up to 39% higher accuracies. But again, as with the other projects, the big message here is how rethinking application operation and really going into model operation in this case let us come up with a solution to tackle a network, or rather an on-path data transfer issue, much lower in the stack, where it would be much more difficult or costly to solve. So I hope I've convinced you about the potential wins we can realize by bringing applications into the purview of the networking community and figuring out how applications work in a deeper sense, and also how that relates to network properties. And in just 2 minutes before I wrap up, I just want to quickly touch on some new opportunities and directions that highlight what this methodology could bring us as a community in the coming years, but also more broadly, what wins could be had by exploring other avenues of deep application network ties. So first, I think that applications can play a very big role in the recent push towards leveraging accelerators like programmable switches or smart NICs, with benefits kind of flowing in both directions, where applications can provide guidance on new tasks to offload to this hardware, and applications can also stand to benefit from the expanded compute footprint that these devices let them run over, right? So they can make decisions from new vantage points or with new information. And second, and more broadly, I believe that applications can be a very large and rich source for networking problems, since they are actually constantly being run in new places, both because the perpetual push to improve them, but also as because underlying platforms are also evolving. Right. So for instance, with things like serverless, many efforts try to take advantage of the parallelism that lambdas bring. But one of the first issues that comes up are these inter-lambda latencies. Or similarly, in resource disaggregated data centers, where you have these pools of remote memory, contention over RDMA links across multiple running applications can be a very big pain point. And applications can actually serve as an avenue for solutions to improve scheduling and sharing RDMA resources. And finally, as more and more interactive machine learning applications push towards the edge, we'll undoubtedly face distributed training and inference scenarios where network delays will inevitably play a big role in performance. I'd like to just take a quick second to thank all of my wonderful collaborators on pretty much all the work that I presented today. The work wouldn't be possible without all of them, and many of them are really the ones that did a lot of the heavy lifting on these different directions. I'd also briefly like to just thank the fantastic set of mentors that I've had over the past decade, since the start of my PhD, then during my time as a professor at UCLA, and now during my time at Princeton. And even more so, a special shout out to just the absolutely awesome, set of students that I've been able to work with over the years, both past and present, that have made this job, just a total pleasure, and who, are really the stars of the show. All right, and with that, I will conclude, and I'm happy to take any questions.
So thanks again for this very interesting presentation. And with the audience, we'd like to thank you again and congratulate you again for the CoNEXT' SIGCOMM Rising Star. Before taking questions. So unfortunately, the camera in the auditorium does not allow you to see the audience. And so when asking questions, I would ask you to mention your name so that Ravi knows to whom he's speaking. So any questions in the room? Let me start with one question. So in your presentation, you saw that you showed that for the web browsing, the parallelism between the data access and the CPU and the network access is causing some delays. I would like to have your perspective on the fact that by adding Quick in the web, we are in fact putting or most of the networking stack inside the application. And is this a benefit from a performance viewpoint, or do you see it as a disadvantage from a performance viewpoint? So the fact that before we had TCP and the application that were decoupled, and now with Quick we can couple everything. Quick being a library in the application, do you see it as a benefit or a drawback?
Yeah, it's a great question. I mean, I think that probably even extends beyond just the web use case. Like, I think people have found sort of use cases for Quick for a lot of other applications, like the video ones that I described as well. I mean, I think that no, it helps, right? I mean, it sort of gives a pathway and a new mechanism to kind of getting to realizing some of the application network co-designs that I was trying to hint at. Right? So it sort of gives a place to sort of embed a lot of that tighter logic. I think what still ends up being hard is figuring out how to actually come up with the right policies for those co-designs, right? Because you have to sort of reason about all of the different ways that an application execution could evolve, and also all of the different scenarios within the network stack. And so if you start to actually if you just take the cross product of those different scenarios, it becomes quite tedious to reason manually about some general policy that will actually work well across all of those. And so I think something like Quick provides a really nice platform to embed some of the solutions that could be, say, data driven, that I was talking about in terms of actually policies for linking those two insights. So I sort of view them as more mechanistic.
Okay, thank you. Questions in the room? So we had some issues with the video. We lost you from time to time for the video, but not the audio, hopefully. So first question.
Hi, this is Marco Melia speaking. Very nice talk, and congratulations again for the award. This is not a technical question. Among the things you have shown, you clearly show the benefit of interplaying within application and networks and bottling and so on. My question is, how many of the great solution you presented, arrive to the product at the end? If you have any suggestion and comment, and eventually how to move from research down to the product and have any real impact in practice.
Yeah, it's a great question. I think that the big drive for a lot of this work, and one of the big benefits I think of kind of bringing applications into the networking purview is this, right? It sort of becomes like a platform through which we can actually like practically realize in very tangible ways a lot of the stuff that we're working on. And right, so like the metrics that people care about in applications really just impact a lot of people. And so it's something that we pushed on a lot. I think that one of the big themes that's actually kind of comes up in pretty much all of the things that I talked about today, and most of my work in general, which I think has helped with this, is sort of moving application developers out of the path of this research. And so in some sense, all of those introspection tools that I talked about they sort of focus on automatically extracting information about, how applications work, and also automatically extracting notions of correctness as they were specified by the developer in the application itself. So the developer is not actually in this process of optimization. And so, I sort of framed it in the talk as being advantageous to us as networking researchers because we don't have to understand all the weeds of the application. But in fact, from a deployability perspective, it means that you can actually apply these to already deployed applications without having to rethink the whole development cycle. And I think that that's one of the big facets of kind of trying to be able to, push some of these into practice. And some of, I think, so for example, some of the model merging stuff at the end that I touched on, and some of the early web work that I touched on had been, deployed at a browser in one case and a video analytics pipeline at Microsoft at the other. And I think, again, a big piece there was just like by letting developers stay out of this, it actually meant that you could put it deployed into a serving platform itself. And I think that that's really a key.
Thank you. Other questions? We are sending the mic to Dario Rossi, who will ask a question.
Hi. So thanks for the talk. One clarification question plus one follow-up. This is going to be technical to change. So I like the part of your talk where you have the ability to fuse different layers of models in order to try to improve in terms of efficiency, memory usage. You also talk about improvement in accuracy. So the clarification there is because you are having the chance to process a higher rate, and so you are getting better accuracy in this term. And then second, more general question is, over there you're doing a work which is system work, appreciable. It's very great. You have any model, then you can automatically try to get the most of it. But isn't there a space for better design of the joint models? If you know that you're going to deploy 4 type of model, one for counting car, one for counting pedestrian, whatever, can we have a common backbone and then multiple heads? So what do you think would be the limit of your approach versus the limit of okay, let's go through the pain of training the models, and what is the efficiency that you can see between the two approaches?
Yeah, fantastic questions. So for the first one, I think your reasoning was spot on. So the reason for the higher accuracy was not because the models in isolation delivered higher accuracy. In fact, accuracies were relative to the base models that we were provided. It's instead just that we were able to process more frames rather than skipping them. For the second bit, yeah, it's a great question. So there's two answers. I think one is for a lot of these video analytics platforms that we've seen in practice, a lot of times models are being submitted by totally different parties. And so coordinating across these does become a little tricky. And if you want to sort of come up with a shared backbone in terms of the way that features are actually extracted, and we found that to be a little bit harder. But I think the bigger issue with sort of just relying on common backbones or stems is, I didn't get to go into this in depth, but what we found is those heavy hitter layers that I mentioned, which are the ones that are actually consuming most memory, are almost always towards the later parts of the models. And so if you were to do a common backbone and you wanted to actually get a big memory saving, you would essentially have to share almost all of the model to realize that, because if you only do like even up to half of the models, which is actually a pretty big stem already, you're missing most of the heavy hitter layers. And so I think that from a memory alleviation perspective, stem sharing sort of faces that big challenge. And so that's why, in contrast with something like compute reduction, I think stem sharing or common backbones is a very, very effective thing to do.
Okay, thank you. We still have time for one question. So the mic is moving slowly.
Hi, thanks for the great talk. This is Stefanos from Brave. I wanted to touch upon the topic of more stochastic workloads, so workloads that you cannot really anticipate. You touched upon the topic with your work on the small short videos, but this also spans across deep neural networks that not necessarily run the whole graph again and again, but they run partially the graph, the DNN graph, I mean. Depending on the input. Do you have any insights towards that and how you can optimize the whole stack towards stochastic workloads? Thanks.
Yeah, that's a great question. I think this is one of the big challenges that's just coming up, I think, in two forms. One, in terms of increased interactivity and modalities for interaction in applications, but also in neural networks, there's this whole wave of dynamic neural networks where you might have a mixture of experts with complicated routing policies. You might be taking multi-branch models or things like this, or multi-exit models. I think what we found, so I think there's sort of two things. I think one, I think some of what we touched on with Dashlet could be helpful. So I do think that in a lot of these different cases, there are still patterns to kind of be had and extracted, not necessarily as formal constraints, but as guiding principles to at least understand how to hedge. It's almost like flipping the issue that we saw with earlier video streaming, where it was really how applications were going to hedge against, total uncertainty in what the network forecast could look like. I think it's going in both directions now, and a large part of it comes down to understanding what you can trust, what you can't trust is a bad word, what you can predict and what you can't predict, and really then weaving in almost just degrees of predictability as opposed to necessarily constraints. And so I think that a lot of in fact, yeah, I totally agree. The second half of the talk pretty much all focused on that. All of the, video filtering techniques as well were somewhat approximate in nature, right? Because they're not formal constraints, and they're instead based on correlations between video features and analytics results. And so I think that it really comes down to figuring out how best to hedge, as opposed to, say, in the web case, how to formally optimize, say, like a graph traversal.
Thank you.
Okay, so let me thank you once again for the presentations and all the answers that you gave, and congratulations again for the SIGCOMM Rising Star Award. And next year the CoNEXT'24 will be in Los Angeles, so I hope that you will be able to join and to discuss with the CoNEXT community. So thanks again.
Thank you very much.